So I'm going to talk about our work on transformation acoustics. These are the researchers that have participated in this project, José Sánchez de Esa, Alejandro Martínez and myself from Universidad Politécnica de Valencia, Carlos Barceló from Instituto de Astrofísica de Andalucía, Jill Jans from Aalto University, and Sante Carloni from ISA.
Could you just face the mic directly?
So this is the outline of this presentation. First I'm going to make a brief introduction. Then I'm going to review the standard approach. So I'm going to make a brief introduction and review the standard approach to transformation acoustics, which we call STA, and some of its limitations. Then I'm going to explain the method that we propose to overcome some of these limitations that we call Analogue Transformational Acoustics, or ATA. And finally I will draw some conclusions. So transformation physics in general is a method that exploits the form invariance of the equations that model a certain physical phenomena under coordinate transformations. So just to briefly review the method, we start from a virtual space filled with a simple medium for which we know the solutions to our physical model. Then we perform, we want these solutions to be distorted in some way, encoded by a certain coordinate transformation. So in such a way that in the new coordinate system these solutions look like we want. But this is just a representation illusion because nothing physical has changed, and we would like to have these solutions but in the original coordinate system. So now we consider a second space called physical space filled with another medium, different medium from the first one, and we realize that the equations that model virtual space in the new coordinate system can be made mathematically identical to those of the physical space, that model physical space, but in the old coordinate system, just by using a special medium here in physical space. Okay, so the first field of physics in which the transformation paradigm was applied was optics, that's transformation optics. And here what we have to engineer are typically the permittivity and the permeability. And the first application that was proposed was the invisibility cloak, which is based on a transformation that opens a hole in space. So after the success of transformation optics, researchers tried to apply the transformation paradigm in the field of acoustics. And to do so, they used the fact that the wave equation for the acoustic pressure is invariant under spatial transformations. It is this equation that we have here. So we can construct limited transformation acoustics formalism based on this equation. To implement a certain transformation, we need to use acoustic materials with special properties, specifically the mass density and speed of sound. But how can these special properties be achieved? And the answer is with metafluids. And metafluids are artificial fluids that are engineered to possess tailor-made acoustic properties. So for instance, imagine that we need a material with some acoustic properties, ρ A and Ca. But we only have a certain fluid with properties ρ1 and C1, and we also have we happen to have cylinders of other material with acoustic properties ρ2 and C2. So what we can do is to fill this homogeneous fluid that we have with a periodic distribution of these cylinders, and use the fact that after a homogenization process, in the long wavelength regime, this microstructure, inhomogeneous microstructure, behaves as a homogeneous effective medium with effective properties that depend on the properties of the constitutive materials, the original fluid and the cylinders, and on how we distribute these cylinders. Okay, so using these two concepts, this approach to transformation acoustics and metafluids, it has been possible to design interesting acoustic devices such as omnidirectional acoustic absorbers or acoustic cloaks. However, this method has several limitations. First, the pressure wave equation implies several restrictions on the background medium. Namely, the background pressure must be constant, and the background velocity must be zero. So we cannot deal with moving media, acoustic moving media, or equivalently, the observer cannot move with respect to the medium. Also, the wave equation is not invariant under general space-time transformations, and many times the required properties to implement these transformations are difficult to achieve with standard acoustic metamaterials like the one that I've shown before. So we realized that to overcome some of these limitations, we need to use a more general wave equation, and we found that the best candidate is the velocity potential wave equation, which is the equation that we have here, because it implies no restrictions on the background pressure. It allows for non-zero background velocity, so we can do transformation acoustics with moving media. It is invariant under a wider class of transformations, and in some cases it turns out that the required medium parameters as derived from this equation are more compatible with standard fluids that the properties required by the standard approach. But it has the disadvantage that it is, as you can see, a quite complicated equation, and which is difficult to manipulate. So to solve this problem, we decided to use some results from analog gravity, which is a research field that searches and exploits analog models of general relativity, non-relativistic research areas, but that exhibit or display as the same mathematical model. So for instance, some phenomena associated to black holes are equivalent in some aspects to non-relativistic waves propagating through a moving medium. And the result that we want to use from this research field is that the one that states that the previous complicated equation, can be mapped to the equation that describes the dynamics of a scalar potential in a relativistic space-time, which is this one, in such a way that all the information is contained in this object, which is the space-time metric, which will depend on the acoustic properties of a medium, and this equation is much easier to manipulate than the previous one. At the same time, we are linking general relativity with acoustic metamaterials. So using these two concepts, the velocity potential wave equation and analog gravity, we constructed our new approach, which I have summarized here. We start from a virtual space filled with a simple medium with these acoustic properties, and described or modeled by the velocity potential wave equation that I mentioned before. Then we use analog gravity to map this equation to the easier equation, relativistic equation. Then we do transformation acoustics, or apply the transformation paradigm in this relativistic abstract space-time, and then use analog gravity to go back to our laboratory space and recover the acoustic parameters of physical space that will allow us to implement a certain transformation. So finally, we have tested our new approach by designing some and simulating some devices. We have designed a carpet clock, but we obtained the same results as in the standard approach, so no news here. We also designed a three-dimensional Maxwell's fisheye, which is a special kind of spherical lens. And it turned out that the properties derived from our method to implement this device are easier to achieve, or are more compatible with standard metafluids than the properties derived from the standard approach. And finally, we designed a carpet cloak, but in a moving background, which is not possible to design with the standard approach because it doesn't allow us to work with moving media. So in conclusion, we have presented a new approach to transformation acoustics based on these two concepts. It has several advantages over the standard transformation acoustics method that I'm not going to repeat. and we tested our theoretical predictions via some numerical simulations.